Okay, so this video is going to be from the static equilibrium homework. It is problem number 4. It states that a 6-meter uniform beam of mass 25 kilograms is suspended by a cable and an 85 kilogram object hangs from the end. What is the value for tension? So I just drew the schematic the same way it was drawn in the picture given in the homework. And now I'm just going to be drawing the forces that we have and labeling what their radiuses are. So we have FG of the block. I just labeled this as FG1, and its radius is going to be the distance of the beam, which is 6 meters. Then we are going to have a second force due to gravity, which is going to be due to the mass of the beam. And this one is going to have a radius of 3, since the mass of the beam is going to be concentrated in the center of mass, which is the center of the 6-meter beam. Now I'm just going to be drawing out the components of the tension in the cable. This is going to be Ty and Tx. It's important that we find some sort of angle to use so that we could use trig, as this will make it a lot easier. So as we could see, this initial triangle with the 75 degrees and 67 degrees, we could find the third angle by adding those and subtracting 180 by them, and we get that angle to be 38 degrees. This forms a complementary angle with this upper one, and that is 52 degrees since they add up to 90. So we know that Ty is going to be T sine of 52, and Tx is going to be T cosine of 52. And the radius, and we're going to be finding the radiuses for these two tensions. The radius for Ty is going to be equal to 4 meters, as that is where it is. As you can see, the 4 meters is clearly labeled. And then I'm just going to create a little triangle right here, because the 4 meters is perpendicular to Ty, but we need to find something that does the same for Tx. So as you can see, we're going to use the 75 degrees to do basic trig. So we get that our radius is going to be equal to 4 times cosine of 75. And then we are going to be looking at the torque formulas to simplify all of this. So we know that the torque in the counterclockwise direction, is equal to the torque in the clockwise direction. So I'm just going to be really quick solving for each sides of the equal sign separately and then setting them equal. So the torque in the clockwise direction, this is going to be caused by the two forces due to gravity. So we have 85 times 9.8. This is going to be equal to FG1, and it has a radius of 6, plus 25 times 9.8. This is equal to FG2, and this is going to be multiplied by the radius of 3. When we simplify this whole answer, we get 5,733. And now we're going to be looking at the torque in the counterclockwise direction. So we have Ty times its radius of 4 plus Tx times 4 cosine of 75. And we can rewrite Ty and Tx. So this could be rewritten as 4 times T sine of 52 plus T times 4 times cosine of 75 times cosine of 52. And ultimately, we can simplify all of this into being 3.79 T. And then we could set this equal to the torque caused in the clockwise direction. So we have 5,733 is equal to 3.79 T. And our tension is going to be equal to 1,512.89. This is somewhat close to the correct answer, but it is not exact. And this is because I did not use the right radiuses. The only one that I did correctly was Tx, but the other ones I assumed that the length of the beam would correspond to the radius, rather than realizing that I needed to do further geometry to find what is actual perpendicular to our forces in the y direction, because the beam is not. So really quick, I'm just going to redraw the schematic that we already had, and I'm just going to be doing some more trig onto it. So as you can see, I'm just drawing out this same schematic. And I'm still going to be labeling these angles that we already found, or that were given to us, I mean. So now I'm labeling my forces. This is still going to be FG1. The force of the beam is going to be FG2, and I'm still going to redraw the components of tension. I have Ty and Tx. And now I'm going to, once again, show the proof for this angle. This is 38 degrees and this is 52. Same process as what I had already done for the first one. Ty is going to be equal to T sine of 52, and Tx is going to be equal to T cosine of 52. Okay, and now I'm going to be drawing this same little triangle to solve for our perpendicular distances for tension. So I'm going to be using the 75 degrees as our angle. This distance on the left, the vertical distance is perpendicular to TX, and the horizontal distance is perpendicular to TY. So the radius for TX is going to be 4 times the cosine of 75, and for TY it is going to be 4 times sine of 75. I just used the 4 meter long beam as well as the angle of 75 and did basic trig. And now I'm creating this bigger triangle. I'm just splitting it up into two, one for FG2 and one for FG1. And the only thing that changes for them is, one, the hypotenuse is going to be 3, that's for FG2, and for FG1 the hypotenuse is 6 since it is the entire length. This angle is going to be 15 degrees since it is a complementary angle with the 75 degrees. So the radius for the 85 kilogram block is 6 cosine 15, and then the radius for the FG2 is going to be 3 cosine 15. So now that we found all of our correct perpendicular radiuses, we could do the same thing. The torque in the counterclockwise direction must be equal to the torque in the clockwise direction. First, I'm solving for the torque in the clockwise direction, which is going to be our FGs. We have 25 times 9.8, that is FG2, times 3 cosine 15. Plus 85 times 9.8, that is going to be the value for FG1, times 6 times cosine of 15. And then we are going to simplify this entire side. It is going to be 5,537.65. And now we can begin solving for torque in the counterclockwise direction. So this is going to be our two different tension forces. We have to include both Ty and Tx because the beam is slanted. So we have Ty, which is T sine of 52, times the radius, which is 4 times sine of 75, plus Tx, which is T cosine of 52, times the radius of 4 cosine of 75. And then we simplified this entirely to get 3.68 T. And we could set this equal to the 5,537. And when we solve for T, we get 1,503.97 newtons. So when you're doing static equilibrium problems, really make sure that your forces are perpendicular with your radius, since that is the definition of torque. And that is how you could be successful with static equilibrium problems.